All right, so we begin again. Still having not fixed the tire problem, but excitement, unexciting excitement. But anyway, so to prove proposition 3, basically you have to walk through the proof that this definition of R module action is actually an R module action. Which, remember what that meant was, for example, if we had R times S acting on x plus n, what's supposed to happen? So that gives us RS, right? Acting on x plus n by the definition. And then, because this is ring multiplication, well, then using the corresponding axiom for the module action on M, this is R acting on S acting on X, right? Using axiom 1 or 2, I forget which one it is. This is by part B of number 2, defining the action, back on page 1 of chapter 10, page 337. Then, logically, this is equal to R acting on S times X plus N, right? Which is R acting on S acting on X plus N. So there you have it. This satisfies axiom 2b. And similar proofs can be given for the other, parts of the module action. And basically, this definition plays nice with the properties of the R module M. Okay, and to show that that's an R module homomorphism is not difficult either. And the fact that the kernel is n just comes from the fact that in the factor group M mod n, the 0 for that group is essentially the set n. Like the coset with representative 0 is the n, and that behaves as the 0 for the additive group. Anyway, enough about that. So you can form factor modules in this way, all right? And then there's also, you can also add modules, in the sense if you have two submodules, if you have A and B submodules of M, then A plus B, which is A plus B, such that A is in A, B is in B, is a submodule of M. Right. And proving that satisfies the, you could go through the submodule test. It would be very fun. It wouldn't be hard, right? If you pick, let me not do that though. You can do that, right?
I mean, it makes sense if you add two things in M, that you get something back in M. But to show that's a submod, it's a little different.
Okay, well, let's see here. If we had X and Y and A plus B and R in the ring, right, then there exists A prime in A, B prime in B, such that X equals to A plus B, Y equals to A prime plus B prime, then X plus RY is A plus B plus R times A prime plus B prime, which is equal to A plus R A prime plus B plus R B prime, which is equal to A prime prime plus B prime prime. And this is using A and B submodules. plus, a prime prime equals to a plus r a prime is an element of A, and B prime prime, A plus B, B plus R B prime, element of B. And then, of course, that's an element of A plus B. So, and also, it's not empty because 0 plus 0 is in there, So it's non-empty. It's closed under addition with the R module multiplication. It's other words, closed under quote-unquote linearity. And therefore, by the submodule criterion, A plus B is a submodule of M. So, yeah. I think any number of things in Calculus 2 are harder than this, okay? Like, agree? I don't know. And then last idea in this section, and of course there are many more examples to read and dumb it and foot that I'm putting on the board here today. Are isomorphism theorems. And Dummett and Foote gives you 4 of them, 4 isomorphism theorems. There's the first isomorphism theorem, which is saying that if phi is a element of the R module homomorphisms from M to N, all right, so think phi is an R module homomorphism from M to N, then kernel phi is submodule. So there's one of the things I was worried about. No need to worry. Kernel phi is a submodule of M, and M mod the kernel of phi is R module isomorphic to the image.
That's our song and dance.
That is the first isomorphism theorem that every linear algebra class should cover, but few do. Let's see here. The second isomorphism theorem as he calls it, all right, is that if you have A and B submodules of an R module M, here's how it goes. A plus B mod B is isomorphic to A mod the intersection of A and B. By the way, you can prove that the intersection of submodules is a submodule. Just like intersection of subspaces is a subspace, right? This one we don't see as much. Third isomorphism theorem. It says that if you have M as R module and A and B submodules with A a subset of B this time, then it's kind of like fractions canceling in the sense that if you have M quotient by A mod M quotient by B, guess what that's equal to? Well, isomorphic to. Care to guess?
Yeah, AB.
Oh, I did it wrong.
Yeah.
My bad. I can't read. Oh, B by A, not A by B. Me dummy. B by A.
M mod B.
Yeah, M mod B. And then the fourth, or quote-unquote lattice isomorphism theorem, says that let N be a submodule of M. There's a bijection between the submodules of M, which contain N, and the submodules of M mod N. And the correspondence is given by A corresponds to A mod N for all A containing N. And this correspondence commutes with the process of taking sums and intersections, i.e. it is a lattice isomorphism between the lattice of submodules of M mod n and the lattice of submodules of M which contain n. So if I had, what that actually means is if you have a picture of the lattice of submodules of a vector space, or module, you can take that lattice diagram and you can like blank out parts of it to see the corresponding lattice diagram for quotients of the module. It's very powerful, this theorem. I think Bill said that there's very little that you cannot prove with this theorem if you have it in hand. Like it will squash everything. And it's essentially it was kind of in the Galois chapter. Like well, it's not exactly that though. I shouldn't say that. All right, so section 10.3. Are we still good?
I'm good.
Okay. So I'll try not to go that long because I need to try to Zoom with my other class, but at least I will scratch the surface here. So section 10.3 is on so-called generation of modules, direct sums, and free modules. On generation of modules, direct sums, and free modules. So first of all, he starts out with a definition. So throughout this section, R is a ring with identity, okay? Not necessarily commutative, but anyway, ring with identity. The sum of modules is defined just like we just did A plus B, right? So that's not surprising, right? If you have N1 plus N2, NK, so that if N1 through NK are submodules of M, that defines the sum of those modules. All right. All right. And for any subset A of M, let RA equal to RA such that R is an R. So it's all R multiples of things in A. Oh, that's not what it is. My bad, my bad. Oopsie, oopsie. My bad. That's not what it is. That's too simplistic. RA is equal to R1A1 plus R2A2 plus RKAK such that R1 through RK is in R. And A1 through AK is in A. And K is an element of, let's say, the natural numbers, yeah? Another notation I might use for this is RA, it's the span over R coefficients of A. That's a sort of a more linear algebraic kind of notation for this idea, but it's the set of all finite R linear combinations of things taken from A, yeah? That's what it is in words. All finite R linear combinations of things from A. Where by convention, if A is the empty set, if A is the empty set, then RA is just the set containing 0, okay? And what else? We will call RA the submodule of M generated by A. Right? You might also not be surprised when I tell you if N is equal to RA, then A is generating set. For N. A is a generating set of N in that case. Or you could say A is a set of generators, right? 3. Right, 3. A submodule N of M all right, is finitely generated. Finitely generated if there exists finite set A such that N is equal to RA. In other words, a finitely generated submodule is one for which there exists a finite generating set. 4, a submodule of M is called cyclic if there exists an element A of M such that N is equal to RA. So in this case, they drop the set notation and just say RA. So it's cyclic, so there's just one. A is an element of N, and R multiples of A build all of N. Okay. He says none of these definitions require that the ring contain a 1. However, this condition ensures that A is contained in RA. Okay. In any event, I think he goes on to explain all of these are submodules. All right. And he says a submodule N of R and R module M may have many different generating sets. All right. For instance, you could always use the totality of N as a generating set for N, right? Like the span of a subspace is a subspace again, right? It's still true here. But what's interesting, of course, is to find a minimal set of generators, right? And if N is not finitely generated, it need not have a minimal generating set. The process of generating submodules of an R module by taking subsets of A and forming all finite linear R linear combinations will be our primary way of producing submodules. Okay, this should be familiar from vector space theory. He mentions, like the span, right? And the abstraction made from the analogous process is so difficult for groups that the abstraction which made the analogous process so difficult for groups in general was the non-commutativity of group operations. For abelian groups, on the other hand, you can do a lot with generators, right? Okay, now he's got a bunch of examples here. All right. Let's see here. Let me erase my isomorphism theorems. Before I get into examples, let me just go ahead and skip over to the direct product definition. All right. No. Definition M1, M2, MK are modules. All right. Collection. This is not the direct product yet, actually. This is, well, excuse me, this is the direct product, external direct product, Cartesian product, you could call it. Then M1 cross M2, MK is the direct product. Of these, yeah? And how do you define the R module action in this case? Like, how do you define R acting on? So things in here are of the form x1, x2, xk, right? That's a typical element in the Cartesian product, where each x sub I is from m sub I. So the way we define the module action on such a thing is just component-wise. And it is straightforward to prove that this definition satisfies the axioms for an R module action, right? So this is just the external direct product, right? So what is it? What's this direct sum? What's a direct sum? So this is just a sum right here. This is a sum of submodules. It's not necessarily direct, okay? So this is also sometimes called an external direct product. And sometimes the notation, sometimes you see notation, sometimes you have M1 is used, all right? External. A direct product. But what's interesting is proposition 5, all right? Proposition 5, which is about internal direct products. And so it's a list of equivalent statements, all right? So the following are equivalent. So one is you have a mapping pi, all right, from N1 cross N2 cross cross NK into the N1, the sum of these. And so here we're assuming that N1, N2, M through K are submodules of M, okay? That's a distinction. In the definition above, the external direct product, there's no interlinking condition between the M1 and the M2 and the MK. They're just separate spaces that all happen to be R modules. Here I'm assuming that the N1 through NK are all subsets of a given R module M.
So,
and I'm giving you a list of equivalent conditions. The one is that this mapping defined by, what's the mapping defined by? The mapping defined by, it's a very silly map, N1 comma N2 NK is just equal to N1 plus N2 plus NK. So that is a, what? Is a isomorphism of R modules. In other words, N1 cross cross NK is isomorphic to N1 plus NK. number 2, independence of submodules. All right. So independence of submodules is this, is that ni intersected with n1, well, let me just write it this way, intersected with the sum j not equal to I of nj is empty. So if you add everything except for the ith subspace together, and then you intersect it with the ith one, you get 0. So in the case of 2 submodules, this just reduces to the condition that the intersection be 0. In the case of 3 submodules, you have the condition n1 intersect with n2 plus n3 is 0, as well as the condition that n2 intersect with n1 plus n3 is 0, together with the condition that n3 intersected with n1 plus n2 is 0. So independence of subspaces, yep. Submodules rather. And then 3, and this is, I think, a nice one, is uniqueness of representation. If X is an element of the sum of these subspaces, then there exists unique nj in big Nj such that X is equal to n1 plus n2 plus nk. You can also, I think, replace this with the condition that 0 in the sum of these spaces is uniquely represented as the sum of the zeros. Well, maybe that doesn't, I shouldn't. Anyway, so the proof of this is involved, but what's that? Now, here's the deal. If you have a collection of submodules that satisfy either 1, 2, or 3, and the additional condition that the sum of them is equal to m, I said it up here. If m is equal to n1 plus n2 plus nk, satisfying 1, 2, 3, right? If it satisfies one of these, it satisfies all of them. That's a theorem following our equivalent. Then we write m is equal to the direct sum of these. And this is known as an internal. It's internal because it's formed by subspaces, submodules of the module. But in fact, to say that a module is the direct sum of submodules, right, is to say that that module is isomorphic to the direct product, just to the Cartesian product of those modules with respect to the natural component-wise module action. It's just that. And so what is a free module then, all right? And our module F is said to be free on the subset A if for every non-zero element X of A there exists unique elements R1 through Rn of R and unique A1 through An of A such that X is equal to R1A1 plus R2A2 plus da da da. In this situation, we say A is a basis or a set of free generators for F, and if R is a commutative ring with the cardinality of A is called the rank of F. Let me put that down here. I think I can erase all this stuff now. Well, oh, this is the nicest. This is the easiest thing to remember. Let's erase this. So free module M is equal to RA, where A is equal to, like, well, I'm not saying it right, am I? A, if for every non-zero element. Well, I got to be careful. I'm not saying it quite right. If for every x and m, all right, there exist R1, R2, Rn in R, and A1, A2, An in A. Now, I'm not saying that A is finite, but I'm saying that you can form X as a finite R linear combination of elements of A. All right. And that's for some n in the natural numbers, all right? In this situation, we say A is a basis or a set of free generators for F. And I think I've missed something here. And I think I was supposed to say free module F. F for free module. There's something I've missed, though, because it's not enough to just say it spans, right? I must replace this there exist here, right? With the following symbol. Yes. Yeah, you add an exclamation point to your backwards E, you're good to go. So there exists unique, right? And that's a basis. Now, and also, say, the cardinality of A is equal to the rank of F. So an interesting question to ask, of course, is when is a module a free module, right? So let's see here. We'll just give a couple of examples here, and then we'll be done for today.
Back to those examples when you said you were going to find them.
I know. I need to do that. But maybe we'll do that now. How about F equal to, like, polynomials over a field, right? Then what's the basis for that?
A naught plus A and X.
No, but it's a set, right? So 1, X,
X squared. Yeah.
right? You could use the so-called monomial basis, right? So what's the rank of this? What's the cardinality of that? Well, the cardinality of this is aleph naught, right? It's the kind of, it's the number of natural, the number of natural numbers, you know?
Yeah.
So, but this is a, polynomials are a free module. Okay. Right, let's see here. Is it cyclic? What's an example of a cyclic?
Not everything generates it though.
Right, I don't think we can pick one. Well, I guess the question is over what, right? So so this is the module over, what was our ring? The ring I was thinking of is the field itself, right? But if On the other hand, I look at the free module of polynomials, right, over the ring of polynomials, then maybe the situation's a little bit different. Then I think I can just use A to be 1, you know, because
Yeah, I was like,
then it's very silly, but f of x is equal to 1 times f of x, right? And so I think that this free module would be cyclic since everything is generated by 1, right? I mean, in the notation over there, this is f is equal to, you know, f of x times the set containing 1. It's very stupid, but this is an example of a cyclic. I mean, a more interesting case, right, of a cyclic submodule would be perhaps vector space, right? So think about V equals to R2, right? And you could look at, so let me that be my module, and let my submodule be, say, span of, you know, the 1, 1 vector. You know, the real span of that. That, I think, is a cyclic submodule, right? Hello?
It's me again.
Where are you now?
I'm at Northport.
Ah, Northport, yes, exciting.
I checked myself over here.
Well, that was relatively fast.
Well, I already talked to the lady. It
Mm-hmm.
took me a while to, of course, mechanics for the department never have anybody sitting there waiting for you.
Mm-hmm.
So they only have 3, hold on. They only have 3 tires. But if you bring in the tire, they will install it for you for $10 a tire. So, which is the same price as Sam's.
Uh-huh.
So, I'm going to go back now and buy the tires at Sam's and bring it over here to install it at 8 o'clock in the morning tomorrow.
Okay.
So it will still be cheap, and we don't need to wait till Monday.
That sounds perfect. So did you book appointment there already?
Yeah, I already booked the appointment for
Okay.
tomorrow. Are you coming home now?
Pretty
Or do
soon.
I have to go haul the, well, pretty soon. I'm not quite sure they're still open. What time does Sam's open here?
Sam,
But now I had to go and somehow put the tires into the vehicle. Oh, it fit, right?
yeah, it should fit. If you put the, I mean, in the back, yeah.
Yes, and then she's like, it's 8 too early in the morning. I was like, no, 8 is fine. I like it to be just out of my way.
Alrighty.
Say that sentence, but that's what it is. So I'm going to go buy tires now.
Okay, love you, dear.
All right.
Okay, bye-bye.
success.
Wow. So we are going to buy,
You taking my idea? Take the tires.
yeah, pretty much. We're buying the set of tires at Sam's Club in Tuscaloosa, and then we have an appointment at the Northport Walmart at 8 o'clock tomorrow morning to get them installed. Whatever. Yeah, and then
Sorry for that.
it's, yeah, she has been all over. It's all my stupid fault. I should have, anyway. So let's see here. So this a line, right? This is a cyclic submodule. So like cyclic submodules of vector spaces, I think, are kind of just one-dimensional vector spaces. I think is that the right idea? Because R multiplication in the vector space is just scalar multiplication. So if your entire submodule is just scalar multiplication of something, it's got to be like a line in your.
Because like
Yeah.
like R 1 by 1, wouldn't it just be the vertical line?
Yeah.
The origin?
Let's.
Or not the vertical line, sorry. The one that y equal to x line going through the origin.
Right. And so another standard thing while I'm on this, if we have V, if you have M equals to R2, yeah, you can take N1 to be R times 1, 1. You can take N2 to be r times 1, 0. You can take n3 to be r times 0, 1. So there are 3 cyclic submodules, if you like, and they pairwise intersect to 0, right? N1 intersect N2, N1 intersect N3, N2 intersect N1 and N3, yeah. So if you were tempted to say that means that those are independent, it would get you into trouble, because then you might be like, oh, so if those are independent, then R2 is the direct sum of those, right? So then that would say R2 is, N1 direct sum N2 direct sum N3, right? Mm-hmm. But this is not the case, because R2 is not isomorphic to N1 cross N2 cross N3. See, each one of these is clearly isomorphic to R, right? And it is definitely the case that R2 is not isomorphic to R3. The problem here is that pairwise intersection of 0 is not a sufficient condition to give you independence. This right here is bogus, since, N1, N2, N3, not independent subspaces. And see, like, what happens if you add any two of these? If you think about, like, what's N1 plus, so here's a picture.
N2 and N3 is N1.
Well, the thing is, N1 is this line, right?
Yeah.
N2 is this line. N3 is that line, right? Well, let me use that line. You're like, haha, I saw that coming. Dang it. You will show up blue. All right, that line. If you take the sum of any two of those lines in all linear combination from vectors that lie along them, you get the whole plane.
Yeah.
So is the intersection of the sum of any two of these with the remaining third 0? No, it's just the remaining third again.
Yeah.
So these are not independent subspaces, and so that's the annoying thing. Like, if a lot of times in linear algebra we just teach for two, like, direct sum decomposition with respect to 2 subspaces, in which case the intersection of them being 0 is enough. But with 3, you have to check for the intersection with not just the other one, but the sum of the other 2.
So, okay,
Yeah,
that's what we were doing before.
Yeah, so these are not, so N1 intersect N2 plus N3 is actually equal to N1 again, which of course is not equal to 0. So there's a cautionary tale about how not to form R2 as the direct sum subspaces. Now, if you just take any two of these lines, right, it is the case that R2 is equal to, N1 direct sum with N2, it is equal to N1 direct sum with N3, it is equal to N2 direct sum with N3. All of those things are true. Because it is true that the intersection of two of them is 0. They are independent, taken pairwise, right? So if you just take two of them, those are independent subspaces whose sum is the whole space. Therefore, they give you a direct sum decomposition of R2, is what we say. We need another example here today to finish things. We need an example of a submodule which is not free. Can we look at an example of a submodule which is not free? Or a module which is not free? Like almost everything you can think of, everything you can think of from linear algebra is going to be free, because the fundamental thing in linear algebra is any vector space has a basis, right? And more than that, you can take any subset of a vector space and you can either reduce it or increase it to become a basis for the space.
Yeah.
So there's incredible results known for vector spaces about bases. How does that break down here? Let's see here.
Well, can't we just take the identity out the ring?
Identity.
Like, since this is since we're modding to a ring, we just take the identity out of the ring, doesn't that kind of thing and everything, like linearity-wise.
Identity out of the ring. But I'm not sure that would still be a module though.
Oh, wait, but I thought we could have. I thought we didn't necessarily. I thought we just needed RNG for module.
But maybe that's the right kind of idea. Like, what if we let the module be, say, I don't know, how about like Z? Oh, that won't do it. Curses. She's got to have an example in here for us. So submodules of a finitely generated module need not be finitely generated. Take M to be the cyclic R module of the polynomial ring with itself.
Z mod 2, direct sum Z mod 2 is not a free C module.
So he's like Z2,
Direct sum Z2.
Z2. So we take that equal to M over what?
It was Z over 2Z. I don't know if that's the same.
Yeah, Z. That's it. This is.
Okay, good.
Yeah. So what was his ring for this module?
Z.
Oh. Okay, and remember, we can make any module a Z module, right? That's always available. So why is Z2 cross Z2 not a free module over Z?
Zero divisors.
Is it, I don't know. I mean, what does this look like? This looks like, what is it? X comma Y, right?
Yeah.
I mean, why can't I just do, this is X times 1, 0 plus Y times 0, 1. So I mean, I could try this, right? That's, I believe, a generating set. I do think it's true that if we look at ZA, yeah, I think, yeah, we get Z2 cross Z2 back again, because I mean, what's the module action here? Well,
pretty much a constant times these two vectors.
Right. So like,
Okay.
so x times 1, 0 plus y times 0, 1 is xy, right? Now here, okay, so I gotta be careful. This is let me use some notation here to clean up, to try to unclean up things. So let's call these the equivalence classes, right? The Z mod 2 Z's. So I'm going to say with representative x and y, all right? So, I mean, to be fussy, the things with blue over underlines are residue classes of integers, right? Goodness gracious. So,
You just said it right there.
where was it?
This paragraph right there. And it has that Y1001 isn't free module.
Mm-hmm. Yeah, I'm trying to understand why.
So,
I mean, it generates it, right?
yeah.
Why is it not a free module then? It's finitely generated, isn't it?
Yeah.
I mean, there's two things in A, and
So each element does not have a unique representation in the form of R1A plus R2A2, where R1, R2 is in R, and A is in M1, and A2 is in M2.
right. So let's be specific here, right?
Yeah.
If you look at the element 0, 1,
Okay.
in Z2 cross Z2. So I see now I owe us these, right?
Yeah.
It is, yes, it is equal to 0 acting on 1, 0, plus 1 acting on 0, 1. But what else is it equal to? It is also equal to 10 acting on 1, 0, plus 17,357 acting on 0, 1 bar. Right? Because that gives us 10 bar, comma, 17,357 bar if you sort through it. But by the rules of mod 2 arithmetic, that's 0 bar, 1 bar. And that's just a taste of it. But so the fact that you can change x, you can shift x by any even number,
Yeah.
and you can shift y by any even number, means that this representation, is far from unique. There does not exist a unique pair of integers x and y. So it's the uniqueness that fails here. It is nevertheless finitely generated. I mean, it just blows your mind. It's finitely generated, yet it's not a free module. I do think, though, if we trade the ring, see if we keep the module the same, however, we change the ring to just Z mod 2. Then this problem goes away. And that is actually the thing I'd like to end with today, which is the quintessential, free module, right, of rank n over the ring R is just Rn. So like Rn, namely R cross Rn fold times, is free module over R with basis EI j equal to Kronecker delta ij. So, and the rank of the Rn is n. So, in chapter 12, as we study modules over PIDs, it becomes very interesting to try to pick off the part of the module which is a free module and the part of it which is not. So it turns out you can write modules over PID as like a direct sum of a torsion piece and a free piece. And the torsion piece is something like Z mod n. And ultimately, finding that in a systematic way is addressed by something called the Smith normal form, which is something like reduced to echelon form, except not just doing row operations. In some senses, like you do rows and do columns. But it corresponds to, well, it's, anyway, more another day. But anyway, thank you for being patient with me. I think we are now, well, we're not caught up, but that's a good place to stop, so.